Here we have an integral whose value depends on x, and we call this the gamma function. And to understand what this integral is doing, I think it's helpful to evaluate for a value. So let's say x is 1, that means you're plugging in 1 in here, and you get t to the 1 minus 1 power, which is t to the 0th power, which is just 1. So this doesn't exist, and you're just integrating e to the negative t, whose integral is negative e to the negative t, and you're plugging in infinity and 0. When you plug in infinity like this, you get e to the negative infinity, which is 1 over e to the infinity, which is 1 over infinity. And that's just 0, right? And anything to the 0th power is 1, so you get 1 as the value. Another integral that you should try is gamma of x plus 1, which means instead of x, you're replacing x by x plus 1, and that simplifies to this integral. Now what you want to do is to try integrating this using integration by parts, and you set u as t to the x power, whereas dv as e to the negative t dt. And I'm using this formula for integration by parts. Integration of u dv equals to uv minus integration of v du. So you need to know what du is. You also need to know what v is. Du is the derivative, and using the power rule, x comes down, and you subtract 1 from the x, which is x minus 1, and then attach dt. And v, if you integrate, this is negative e to the negative t. Put on the right side u times v, which is t to the x times negative e to the negative t. That's what I wrote here. That's uv. And then v du would be this times e to the negative t. And this minus now became plus because of this minus. So minus of minus is plus. Now, if you try to see what you get if you plug in infinity, you get infinity to the x power times e to the negative infinity, which is like negative infinity to the x power over e to the infinity. And this is really a competition between, just think about some value of x. Say x is like 4th power, and you have t, and then e to the t. It's a competition between a polynomial growth and exponential growth, and exponential growth grows faster than any polynomial, so when you send t to infinity, this is going to go to 0. And if you don't believe this, you can also try using the L'Hopital's theorem like 4 times, and you can show that this is equal to 0. So you can get this value as 0, because if you plug in 0 into t, then that also gives you 0. And yeah, and actually I'm assuming that x is positive. Okay. Now another thing that you see is that x here has nothing to do with the integral dt. It's like a constant when you integrate, so I can bring it outside the integral. So you have this, and after doing that, you see that this is exactly the definition of the gamma function we had. So the final result is that gamma of x plus 1 is same as x times gamma of x. Now these two results that we just figured out has a very important implication, which is that gamma of n plus 1 is equal to n factorial. Now let's see why that is. See, if I say gamma of x plus 1 is equal to x times gamma of 1, for example, gamma of x, for example, then if I have, say, gamma of 4, I can apply this formula over and over again. So gamma of 4, it would be like 3 being x, right? Because 3 plus 1 is 4, and that's 3 times gamma of 3. And gamma of 3 is, again, using 2 here, then gamma of 2 plus 1 is 3, just as I wanted. But that's same as 2 times gamma of 2. So this is like 2 times gamma of 2. Gamma of 2, again applying the same reasoning, this is 1 times gamma of 1, and we just established that gamma of 1 is 1. So it's just 3 times 2 times 1, which is 3 factorial. And you can see that this kind of argument can be done for any integer value. positive integer value, and you end up with this. And this actually reveals the reason why we need the gamma function. The gamma function is a way to generalize the factorial so that you can talk about factorials of non-integer numbers. Once you have gamma functions, you can talk about something like a factorial of a half. I mean, nobody knows what factorial of a half is, right? It doesn't make any sense, but you can think of this as gamma of 3 over 2. Okay, because n factorial is n plus 1 of gamma of n plus 1, so 1/2 factorial will be 1 added to 1/2, so gamma of 3 over 2. So you can generalize factorials to some other numbers. Here are some facts about the gamma functions. And unfortunately, much of these facts has something to do with complex analysis. So if you haven't learned complex analysis, not much of what I'm saying will make sense to you. So if you want to understand more about gamma functions, it would be nice to have like a one semester course of complex analysis. Then you'll be able to understand what these are doing. So there are many words from complex analysis, such as analytic continuation, meromorphic functions. So gamma functions, this integral is not always defined, but once you have this defined on, say, the positive real numbers x, then you can use something called analytic continuation so that this is defined for most of the values, even for x being complex numbers like I. You can plug in I and you can still make sense of this by using this analytic continuation. Now the second fact, gamma of 1/2 is square root of pi. That's interesting. We just talked about 1/2 factorial, right? I mean, this is not an accepted way to write factorials for non-integers, but like, let's put this in quotes. 1/2 factorial. What does that mean? That's gamma of 3 over 2, and because this is 1/2 times gamma of 1/2, if we know that gamma of 1/2 is indeed square root of pi, then we can kind of say that 1/2 factorial is square root of pi over 2. Yeah, and you can come up with other values of half integer factorials this way. Now, to actually prove this, you need to use calculus 3 methods, and the way people do this is by doing some u substitution with this fact that e to the negative x squared dx from 0 to infinity. Can't quite recall. You do this by using double integrals and using polar form, and it does take a while. If I actually took the time, I can do it, but since I just want to give you an overview, I'll leave this to either some online PDF files or other YouTube videos you can find. Okay, number 3, unfortunately, even if you extend this into all complex values, this is what we call meromorphic function. Meromorphic means that it has some values where the function value doesn't exist, and for gamma functions, it happens to be that at 0 and any negative integers, so here I'm assuming that n is positive, these are undefined, and it has something called simple pole, which if you again took complex analysis you would understand, but if you didn't, don't worry about it. And there are some other nice formulas, much more than this, and all of the proofs for these require complex analysis. Now let me try to explain what I mean by this being undefined by showing you the graph. Here's the graph of the gamma function. As you can see, we know that gamma of 1, we prove that it's equal to 1. Gamma of 2 is equal to 1 factorial, which is all again 1. Gamma of 3 is 2 factorial, which will be 2. Gamma of 4 is 3 factorial, which will be 6, somewhere here, 6. So it will give you all the factorial values at integers, and it's smoothly connected. The downside is that at 0, it's not defined. And there's a actually very good reason why for 0 it won't be defined. The reason is that we know that gamma of x plus 1 equals to x times gamma of x. So if I solve this for gamma of x, we know that gamma of x is gamma of x plus 1 over x. And let's say you're taking the limit of x going to 0 plus. Well then, the left side, what you would like to be gamma of 0 would be gamma of 1 divided by 0 plus, because x goes to 0 plus, right? But gamma of 1, we just proved that it's 1, so it's 1 over 0 plus, so it's in positive infinity. So we kind of see that as you evaluate gamma of x with x going to 0 from the right, it has to go to positive infinity. There's no way around it if you want this identity. Okay, so that's why you have a pole, and the other ones, well, I guess if it's infinity and you still have this, you might need some infinities here too. I didn't check that, but well, anyways, this integration would have these infinities. Okay, now Gauss was not so happy apparently of the fact that gamma of n plus 1 is equal to n factorial. He didn't like this, so he actually shifted this. He replaced x by x plus 1 and defined this as his function pi of x. And if you use this definition, then pi of n is exactly n factorial. And that would have been pretty nice too, but apparently for some higher mathematics, there are formulas where gamma function makes it easier than the pi function. So somehow I didn't quite get into that detail. There are some examples where gamma is easier. So even though this seems like a better choice, people are stuck with the gamma function. Now, if trying to mimic the factorial values and just connect it into a continuous function is the only aim, only goal, then a legit question could be that, is this the only way to generalize the factorial for non-integer values? And the answer is no. Hadamard made this gamma function, which actually gives you factorials exactly for integer values, but nice thing is that it doesn't have these poles. It doesn't go to infinity. It's like all connected. But because being infinity at 0 is a consequence of having this identity, as I said earlier, x of gamma of x should be gamma of x plus 1, we will know that these functions won't satisfy this type of identity, and it will only satisfy this identity for positive numbers or positive integers. Nonetheless, sometimes people might want this, right? So there are people who have thought about this question, and if you want to know more about these other types of factorials, gamma functions, then search Peter Lushny. He has an article called "Is Gamma Function Misdefined?" And if you read it, you'll see some other definitions of some other approaches. But even after reading his, I can see that the gamma function is like the simplest integral that you can write down to mimic the factorial, so I'm just happy with just knowing the gamma functions. Okay. Now let me close with some nice things about the gamma functions. So what's great about having the gamma function? What good does it do? Well, the first nice thing about gamma function is that when you solve differential equations using power series methods or Frobenius methods, often you get these factorial-like expressions but it's not really integers. So for those, you can have gamma functions. It helps if you have gamma functions. Here's a Bessel function, which is the solution to Bessel's equation, and as you can see, it gives you this, and this nu can be any number. It could be any positive number, or if it's a negative number, it can't be an integer. But if you have that, then you can define it like this. Okay. Another thing is there's something called hypergeometric function, which are solutions of more general differential equations. Secondly, there is a way to use this integral representation to get the approximate value of the n factorial, which is nice. I mean, there are ways to approximate this using some, again, it's not so simple. It uses some complicated mathematics, but if you do, then you get this nice approximate formula, which is that n factorial is similar to square root of 2 pi n times n over e to the nth power times 1 plus 1 over 12n. And such approximation is very helpful if you have to estimate some complex formula, or sometimes if you need to figure out if a given series converges or not. Having the Stirling's formula is very helpful. And thirdly, other formulas in math are easily expressed by gamma function. For example, volume of an n-dimensional unit ball is given by this with a gamma function. So for example, a two-dimensional ball is like, it's a flat disk. So two-dimensional disk is equal to pi r squared. That's the area, right? But since it's a unit, meaning r is 1, that would mean that the area would be pi. And indeed, if you plug in 2 for n, you get pi 2 over 2, which is first power, gamma of 2 over 2 plus 1 is gamma of 2. Gamma of 2 is 1 times gamma of 1. And gamma of 1 is just 1, so it's equal to pi. So you do get that. So it will be interesting to apply this formula for other values of gamma, and try playing with this. Of course, there are proofs for this, which I won't go into, and those are some exciting things that you can learn about. So that's all I have for the gamma functions, but it's very rich. You have so many other things that you can learn about gamma functions. So try learning some more gamma functions by books or some other videos.